argument is y greater than 0, then this is equivalent to y greater than 0. And the fourth condition, this means y less than minus 1 and y less than 0. This is equivalent to y less than minus 1. Okay. Then, if y is equal to minus 1, or y is greater than 0, or y is less than minus 1, in all these cases, our equation admits solution in which all the elements of the range of f. Then, we can prove that the range of f is a game joint. All the real numbers which are less than minus 1, and all the real numbers that are
If the f is
That means that assigns the same value to minus x as opposed to x. What that means for the graph is that the graph displays a certain symmetry. The graph is symmetric, we say, with respect to the y-axis. The meaning of this, if we look at the right-hand branch of the graph, when we rotate it around the y-axis, we come upon the left-hand branch. This is symmetry with respect to the y-axis. So here's our function, and there's its graph. If I ask you, is g an increasing function? Well, clearly not. G decreases when you're on the left, so y decreases when you're on the right. However, let us observe that if we were to restrict attention to the positive x's, then it would be an increasing function. So we could restrict attention to r plus, as it's called. Standard notation, r plus means the positive numbers in r, the interval 0 and infinity. More generally, we have the following proposition. For any positive integer n, the function phi, defined to be the nth power of the argument, is a strictly increasing function on r plus. Here, of course, x to the n, or x power n, nth power of x means x multiplied n times. That proposition we're now going to prove because we haven't had the fun of doing the proof in a little while. Here's the proof. It's my induction. We want to first prove it for n equals 1. We want to prove that the function x matched to x is strictly increasing on r plus. That amounts to checking x less than y implies x less than y. Well, that's pretty evidently the case, so the case n equals 1 has been disposed of. Next, and finally, we have to prove that whenever x to the power n is strictly increasing on r plus, the same is true of the next power, n plus 1. When we take two numbers, x less than y, we find something that will show is inequality. That power is certainly true if x is 0, so let's assume x is 1. So we have x n less than y n. If we take that strict inequality and multiply it by the strictly positive number x, we'll obtain this, which I want to save for later use. Similarly, if you take the same inequality but now multiply it by y to the n, you get this inequality. Now let's combine the two inequalities we've obtained in a string of relationships. And you can see that we have the first and we have the second. And if you now look at just the extremities of these relations, you see that we have proved that x power n plus 1 is less than y power n plus 1, which is exactly what was required to prove. So that's the end of the proof. They used to say QED at this point. Now we put this symbol, so perhaps we should say box or end of proof. We continue our study of graphs. Let's look at the function x cubed, that is x to the power 3. I call it h here. We can trace its graph as we've done for other functions, and you get something like the following curve. Does that curve look odd to you? Well, the function h is odd. H of minus x is the same as minus h of x, as you can check. This property of the function gives you a kind of symmetry, different from the symmetry about an axis that we saw earlier. This gives you symmetry with respect to the origin. The meaning of that is the following. If you take a point xy on the graph, if you proceed to draw a straight line from xy through the origin, you will meet the point minus x minus y, and that point will also be on the graph. Now we know from an earlier proposition that the function h is strictly increasing on r plus. But given this symmetry, we can go on to deduce that h is actually strictly increasing globally on the real line. Another function of interest is the function 1 over x. It's clear here that we have to restrict the domain, right? We have to avoid the value x equals 0. When we draw the graph of the function, we get something like this. And this curve, the red curve, has the property that as x moves out far to the right, the red curve gets closer and closer to the x-axis without actually meeting it. We say that the x-axis is a horizontal asymptote of the curve. You notice that the function capital F here is an odd function. Therefore, in order to have the left-hand branch of the graph, we can apply symmetry with respect to the origin, and we know it's going to look like this. Look at the behavior of this function at x equals 0, where it's not defined. As x approaches 0 from the right, getting very, very small, you can see the value of the function gets bigger and bigger and goes up to plus infinity, asymptotically. Similarly, as x approaches 0, but from the left, the value goes down to minus infinity, asymptotically. We say that the y-axis is a vertical asymptote in this case. Sometimes functions are defined in a piecewise manner. They have two different defining formulas, depending where the arguments are. For example, you could have a function f that agrees with g if x is less than k, but then switches over to a different function h when x is greater than k. You know, we already have an example of such a function. The absolute value function is of this type. It's given by minus x when x is negative, and by plus x if x is positive. How do we find the graph of absolute x? Well, we could look at the graphs of the two components, the functions minus x and x. Those are affine functions, so we know how to graph them. And then we take the left-hand branch of g and the right-hand branch of h, put them together, and you have the graph of the function absolute x. Let's speak now about dilation. Dilation means multiplication by a constant. What happens to the graph of a function when you multiply the function by a constant c? Let's take our familiar example, the x squared function with the parabola being the graph. What happens if we multiply the function by a constant bigger than 1? Well, the answer is the graph will sort of be expanded. It will be dilated upwards because c is bigger than 1. If we multiply by a positive c that was smaller than 1, then the graph would be dilated down. It would get squished. What about negative constants? What if the graph of this function were multiplied by minus 1? In that case, the graph of the new function would be rotated relative to the x-axis. Whenever this positive becomes negative, that would be the graph of the function minus x squared. Another way to alter a function is by translation. For example, one can just add a constant k, a fixed real number, to the values of f. In that case, the graph of f will be vertically translated.
That means vertically shifted, up or down depending on the sign of k. Here's an example. What is the graph of the function x squared plus 1? Well, we know the graph of the function x squared. It's our parabola. And if you want to know the graph of the new function, you just take the old one and shift it up 1 unit, and that'll be the graph of the new function, x squared plus 1. Another way to apply translation is inside the function. Given an argument x, we're going to apply f, not at x, but at x plus k, where k is a fixed real number. In that case, it turns out the graph of f will be horizontally translated, left or right. Let's look at this example. What is the graph of x plus 1 squared? Well, if the x plus 1 were the real variable, let's make a change of variables and call x plus 1 capital X. In that case, we would know exactly what the graph looks like in terms of capital X. That would be it. How do we relate that to what the graph should be in terms of our real variable, the lowercase x? Well, the key is to note that capital X equals 0 in the change of variables corresponds to little x equals minus 1. That's where the origin should be shifted to. So we take our graph, we shift it to minus 1, and that is the graph of the new function x plus 1 squared.
Exercise of the graph of the function practice step. You have to prove that the function f x to x cubed, g x to 2 times x cubed, h x to 1 over 2 x cubed are strictly increasing and odd. While the function f prime x to minus x cubed, g prime x to minus 2 times x cubed, and h prime x to minus 1 over 2 x cubed are strictly decreasing and odd. You have seen in the previous video that the function f, which sends x to x cubed, is strictly increasing. It is that if x is less than y, we have that x cubed is less than y cubed. Okay, now let us consider two cases. If a is any real number greater than 0, and x is less than y, then we know that x cubed is less than y cubed, and multiplying on both sides by the positive real number a, we get that ax cubed is less than a y cubed. Therefore, considering a equal to 2 or to 1 or 2, we get that both g and h are strictly increasing. On the other hand, if a is a real number less than 0, then what we get if we repeat the similar reasoning? We get x less than y implies x cubed less than y cubed, but now multiplying by a negative number on both sides, the disequality reverses, and we get ax cubed greater than a y cubed. Therefore, considering a equal to minus 1 or minus 2 or minus 1 over 2, we get that the functions f prime, g prime, and h prime are strictly decreasing. Okay, and now because if this function are odd or not, what needs to be an odd function? Okay, we have for f, g, and h, we have to check which is the image of minus x. Precisely, f of minus x is equal to minus x to the cube, which is equal to minus x to the cube, which is equal to minus f of x. Therefore, the function f is odd. Similarly, g of minus x is equal to 2 times minus x to the cube, which is equal to minus 2x to the cube, which is equal to minus g of x. And then also g is odd. Now h of minus x is equal to 1 over 2 minus x to the cube, which is equal to minus 1 over 2x cubed, which is minus h of x. And also h is an odd function. What about now f prime, g prime, and h prime? Let us compare again f prime of minus x with minus f prime of x. It's equal to the others. Then we have f prime of minus x is equal to minus x to the cube, which is equal to x to the cube. And what is minus f prime of x? It is equal to minus f prime of x is minus x cubed, which is equal to the x cubed. Therefore, these two are equal, and then f prime is another function. Now, g prime of minus x is equal to minus 2 minus x to the cube, which is equal to 2 times x cubed. And minus g prime of x is equal to minus 2x cubed, which is equal to 2x cubed. Again, g prime of minus x is equal to minus g prime of x, and then g prime is another function. H prime of minus x is equal to minus minus 1 over 2 minus x to the cube, which is equal to 1 over 2 x to the cube. And minus h prime of x is equal to minus 1 over 2x cubed, which is equal to 1 over 2x cubed. Again, h prime of minus x and minus h prime of x coincides, and therefore also h prime is an odd function.
Spend some time looking at functions defined by powers. As is often the case, we begin with integers, integer powers. For example, we've seen the function x squared in the past. We need some terminology about how things work with powers. If you have an expression like a to the power n, a is called the base, and n is called the exponent, or the power. Some facts about these concepts are the following. Let's fix two integers m and n positive. Then we have all these rules for powers, which are actually easy to prove in the case of integers. I'll let you look at them for a moment. Perhaps they look familiar to you. If you were to prove them, they would follow from the commutative law in arithmetic and the associative law that we saw some time ago. Now, these facts need to be second nature to you. If they're not already, well, doing a million exercises will really help you remember them. Two specifications. A to the power 0 is always defined to be 1, provided that a is non-zero. And 0 to the power 0 is just not defined. There's no way to define it so that things work out. What are the graphs of these power functions going to look like? We already know two of them. X squared, the parabola, x cubed, that we saw not long ago. We see that for n even, we have a function that is increasing on our plus, whereas for n odd, x cubed, we have a function which is globally increasing. Also, the x squared was an even function, the x cubed was an odd function. Well, these things carry over to other powers. For example, x to the fourth is an even function, which is increasing but only on r plus. It looks a lot like the parabola, but you notice it's much flatter near 0. It's not a parabola. X to the fifth has roughly the same nature as x cubed, and so on. If you zoom in a bit on the first quadrant, you see that the two functions xm and xn agree at x equal 1. All these functions do. They have the value 1 there. The x to the power m, the smaller of the two powers, well, it's higher than the other when you're between 0 and 1, but then it's lower when x is greater than 1. How about negative integer powers? We can define those. Here's how it's done. We take an a different from 0 to avoid division by 0, and we define, as usual, a to the 0 equals 1, and we define a to the power n, where n is a negative integer, by definition is equal to 1 over a to the power minus n. That's already defined because then minus n is a positive integer. Now, why do we define a to the 0 equal 1? Well, here's one explanation. We would like this law of exponents to still work for 0. And from what I've written down, you can see that this forces a to the power 0 to be the identity element for multiplication, that is 1. Otherwise, this law would fail to hold. Similarly, we have to define a negative exponent base this way, because if we want this law to hold, then a to the minus n has no choice but to be the reciprocal of the other value. For example, what is pi to the power minus 2? It turns out to be 1 over pi squared. What is pi to the power, minus pi rather, to the power minus 3? Answer, it turns out to be minus 1 over pi cubed. Let us note that the following expressions are never defined. 0 to the 0 or 0 to a negative integer power. These facts all hold for integers, which now can be negative as well as positive. And I have some good news. Visually, these facts are exactly the same as they were for positive integer powers. Therefore, we already know these facts, sort of. Anyway, visually they're the same. Let us now turn to the graphs of powers.